Hello, I'm excited to share with you today the ACI chapter of the University of Florida's response to the Concrete Solutions Challenge. We begin with a subject that is consequential to our ocean's environment, coral reefs. Coral reefs' most important contribution to our planet's oceans is the fact that over a quarter of all aquatic life in our oceans directly depends on reefs for a myriad of necessities. Whether it be shelter, food, or a reproduction site, reefs are paramount to life in our oceans. To put it plainly, reefs are the consolidation of color and life in a comparatively barren ocean. However, coral reefs don't just benefit the organisms down in the deep blue sea, they're also extremely valuable to humans too. The economic activity associated with fishing and diving around reefs is estimated to be in the tens of billions of dollars each year. The income associated with reef contingent businesses greatly impacts over 500 million people worldwide, as well as providing protection from oceanic erosion, which impacts even more people worldwide. That's what makes the drastic decline of our reef ecosystems even more troubling.
Coral reefs are endangered by natural phenomena such as hurricanes, local threats such as overfishing, destructive fishing technique, coastal development, pollution, careless tourism, and also climate change, which causes sea temperatures and levels of CO2 in water to increase. About 75% of the world's coral reefs are at risk from local and global stresses. About a quarter of them have already been damaged beyond repair. If we don't start taking care of this issue, about 90% of coral reefs will be endangered in less than 10 years, and nearly all of them by 2050. A recent study of 159 reefs in the Pacific Ocean found that plastic pollution is killing coral too. When coral reefs come in contact with plastic waste, the incidence of disease rises. Scientists say that the bacteria on the plastic can infect the coral, and the plastic can block the needed sunlight. By 2025, they project that 15.7 billion plastic pieces could come into contact with coral reefs. Furthermore, climate change causes sea level to rise and resulting in drowned coral reefs and more intense storms that produce excessive nutrients and sediment runoff. Finally, 22 million tons of carbon dioxide is absorbed by our oceans every day, changing the chemistry of seawater and increasing their acidification. Today, coral reefs experience more acidity than ever in history, reducing the water's carrying capacity of calcium carbonate that coral needs to build their skeleton. Even this small decrease in the coral reef's ability to construct skeletons leave them vulnerable to erosion.
The concept of utilizing concrete to help grow coral reefs is not new. Artificial reefs are commonly used structures that are utilized in order to provide a stable platform to encourage coral growth. In the Philippines, a project called Acandasia is aiming to revitalize coral reef structures through the use of a concrete substrate. Concrete is an especially effective coral reef substrate as it is durable enough to survive in rough ocean conditions while incorporating chemical properties conducive to reef survival, such as the presence of calcium bicarbonate, as well as a low chance of contributing to ocean acidification. All of the images on this slide are of Acandasia in use, so you can see here that concrete actually does help coral grow. Putting concrete in the ocean is also not a new concept, as concrete ships were commonly used throughout World War I and World War II. During the wars, concrete ships were built in an effort to ease supply constraints for valuable materials, such as timber, aluminum, and steel. 12 concrete ships were built for World War I, and 24 more concrete ships were built for World War II. After the war, many of the ships were decommissioned and utilized as breakwaters throughout the world. In this instance, concrete was an excellent choice for a building material, as it was able to resist wave action, perform as a strong and durable material, and still maintain buoyancy. All of these characteristics would be very valuable for a concrete buoy. The images on this slide are of a concrete ship, as well as a plan for a concrete ship.
While designing the buoy, we primarily focused on meteorological applications. To account for this, we gave the buoy as large a top surface area as we could so that a wide array of instrumentation can be mounted on a single buoy at one time. In addition, this buoy design can be scaled down to fit other maritime navigational needs, such as channel markers. This exploded view clearly shows the three main parts of the buoy. The removable bottom aluminum flange that allows for easy exchange of the concrete hull in the event of concrete hull failure, the concrete hull itself, which should fall to the ocean floor at the end of its lifespan, generating an artificial reef, and then the aluminum instrument base. The aluminum instrument base will be tethered to the seafloor using an anchor and chain, and in addition has 3 aluminum ballast to keep it afloat in the event of hull failure. The aluminum ballast have the added benefit of decreasing the amount of foam needed, which could further contribute to ocean pollution if it were destroyed.
The Florida Fish and Wildlife Conservation Commission does not regulate the required materials used for buoys or floats for recreational and fishing activities. However, it has strict specifications for the allowable range of the visible height above the water. The commercial buoy market is dominated by buoys made of primarily 2 materials, polyethylene and polystyrene foam, otherwise known as styrofoam. Polyethylene does not break down into microplastics and is very durable in marine environments. Styrofoam can easily break down into microplastics, but does not degrade for hundreds of years. So it biomagnifies and accumulates through the food chain. When these foam buoys become detached or abandoned, their assimilation into the marine environment is not beneficial. Many studies have found that derelict fishing buoys account for a significant amount of marine litter and microplastics in our oceans. Our proposed buoy, if it detached or abandoned, would help propagate new corals, serving as a viable substrate and source for strengthening existing shelled organisms.
The synthesis of all this information makes it clear. The potential for concrete buoys is more than just some aesthetic change. It is an innovative look into the future. In the paper, Artificial Reefs, a review of their design, application, management, and performance, Mark Bain comes to the conclusion that, coinciding with materials costs and other regulatory measures, quote, much of the problems that have arisen in case studies has related to general planning and management issues, end quote. The solution presented offers an expansion on the already existing concrete reef technology, which serves to minimize the effects of reef decline.